Well, good afternoon, everyone. Um, Today is going to be the last exam review prep or exam review. So this is actually set up as your final exam. If I had to be totally transparent, the format is exactly the same. It's going to be 30 questions, multiple choice, short answer. That's electronically given as a multiple choice and true false. Again, 30 questions, very same format as last time. The exam split about 20 questions about material covered since the last exam, and 10 questions that basically key on key topics, key things we spent a lot of time on during the semester. So if you only studied material since the last exam, you're probably in pretty good shape, I think. All the files are online, all the live lectures are online, everything's posted for you to read, you read and watch. Uh, a very significant portion of the questions for this exam are based on questions that came about in recent worksheets. So preferentially focus on materials since the last exam, but there are major themes and content from prior exams and weekly worksheets are fair game. What I'm saying there is that if you look at the questions that are in the prior worksheets, that should be enough for review of the materials for the final exam. The exam is going to open here on Friday. I originally was going to do it in December, but I'm open here on Friday, November 27th. Give everyone a chance to read the exam review and ask me questions. It's open the 27th. It'll be open until the exam period is over on December 9th. As you get done, I should be able to post your final grades not very long after that. So if you want to get it done and get it out of the way, if you're leaving campus, it should be straightforward to do so. So without any further ado, I'll jump into the topics. I'm going to cover first topics that were new since last exam. Key and other things I'm going to probably most likely include on the exam, and then we'll go over a couple of key topics towards the end that are the key things I want you to focus on from beforehand. So it's not going to be surprises. Should be pretty straightforward. I hope you all do really well based on performance in the last exams. I expect everyone absolutely will. All right. So the topic that we actually was split between the third and fourth exams were water quality. Remember the key things about water quality: contamination, unsuitable water quality, pollution, human-induced decreases in water quality. That's an important aspect. Where we really left off was talking about natural contamination. So natural contamination of water quality can impact up to about 3 billion people per year on planet Earth. 2 billion people are impacted by naturally occurring arsenic contamination alone in relation to sediments that are rich in arsenic that is then released in the alluvial sediments from the Himalayan mountains alone. So we're talking here India, Bangladesh, Pakistan, and other regions over to the southeastern Asia that receive sediments from the Himalayas. Those sediments actually lead to about 2 billion people a year being impacted by arsenic. Key punchline with this is that naturally occurring contamination can impact a lot of people. And then one of the things I covered in the water quality is again that biochemical oxygen demand is a common measure of the quantity of organic matter in water. So this is actually an area from the water quality that's really relevant to the full component. So this is something I'm highlighting across the whole course. That this is one of the metrics when people buy a home, people go to look at an area. And one of the first things people look at often is the oxygen levels. Look at the biological oxygen demand as a measure for water quality, and I want to make sure you know about that so you can avoid buying a house or something like that has bad water in it. Really, where we went after that on water quality, we talked a little bit about as well as naturally occurring contamination. We talked about naturally occurring methane contamination and methane releases from hydraulic fracturing. I'm going to cover those in the fossil fuel section here in a few minutes. So I'm going to move on to energy consumption, which is actually where we spent a lot of our time during lectures talking about electricity consumption in the U.S. So like water demands, like mineral resource demands, we're going to talk about a little bit later. Electricity consumption in the U.S. has been increasing for at least 60 years. The two dominant fossil fuels burned for electricity generation in the U.S. are coal and natural gas. Coal remains the most prevalent, although its role has actually decreased. That decrease in coal usage for electricity generation has been offset largely by natural gas usage for electricity generation. So just remember, in essence, there's been a redistribution amongst the fossil fuels, and there's been a redistribution amongst renewable energy. But actually the percentages of fossil and renewable energy for power generation have pretty much offset. Hydroelectric's been decreased, solar and wind have increased, coal's decreased, natural gas has increased. Okay, but the reality is power generation hasn't really moved away from fossil fuels just yet. So the percentage of coal, let's just say, coal in electricity generation has decreased over the last decade. However, the change has been offset by increases in power generation from natural gas. Okay, and then I guess I already said this. The distribution of renewable energy has been changing. Percentages remain nearly constant, 10%. I do think 10% is a number you ought to keep in mind. Well, there's a lot of hope this is going to change and change dramatically in the next 50 years, next 20 years, next 10 years. The reality is we're starting out from a basis of nominally 10% renewable power, which has only been redistributed internally, not actually moved out of the non-renewable sources. I'll state again, if only renewable energies can encompass the new electricity demands, the per capita energy demands that are sort of baked in at this point in time, that would be a pretty major win. We're optimistic about removing fossil fuels, but realistically, curbing them off and having new power generation coming from electric is a very important part of this. The price of natural gas after the advent of horizontal joint manufacturing has displaced nuclear power. So in essence, if you want to think about this on fossil fuels, the renewables, of purely renewables, have actually remained about the same. But there's things like nuclear power nuclear power, hydroelectric power, they've actually had their utilization slowed by the advent of natural gas development. Wind and particularly solar have done reasonably well, but largely at the expense of nuclear, hydroelectric, and others have been largely at the expense of low natural gas prices. So despite the fact that solar wind increasing, again, there hasn't been a change in the percentage derived from renewables. I've hit this a couple of times. You're probably getting the idea. This is going to be on the exam. But one of the key benefits of this is that the U.S. during the last decade has actually experienced a decrease in CO2 emissions. So basically, CO2 emissions have actually decreased during the last decade. That started in the economy changing in around 2008, 2009. Manufacturing has been continuously leaving. There's been increases in fuel efficiency, and quite frankly, there's been a transition from natural gas from coal, and all those things actually reduce CO2 emissions. Although there is controversy about the role of methane levels increasing the atmosphere and how that might play a role in greenhouse gas emissions and climate change. So all forms of fossil fuels are formed by the degradation of organic matter. In coal, that organic matter is often sort of leafy plant-like material that's formed by the degradation of organic material in swamps and shallow coastal marine areas that gets buried with increasing pressure, but also temperature. You can see a transition from peat to lignite to bituminous coal and anthracite coal. I won't test you on those names at all, I don't think. But the key thing is for coal, it's usually derived from organic matter. In oil and gas, it's plants in that situation that are drawing down CO2. In the case of oil and gas, it's typically bacteria, algae, and plankton in marine or lacustrine environments who are sucking that down, sucking down CO2 and actually making organic matter. So that's a little bit different source, but all the fossil fuels use CO2, store it as an organic matter that gets buried in either marine environments or lakes or nearshore environments in the case of coal, that with enough heat and pressure converts to oil and gas or coal respectively. Obviously, the main issue of concern with fossil fuels is greenhouse gas emissions have a major environmental impact of the fossil fuel usage. Climate change is something we talked about earlier this semester. It's a huge issue, and it remains a big concern regarding using these fossil fuels. If you look at some of the derivative components, one of the issues the last generation has really been, it's sort of been kind of mitigated during most of your lifetimes, I think, but it's actually caused by acid rain. And acid rain is the scenario where you burn oil, natural gas, but particularly coal, which is rich in sulfur and nitrogen. The combustion of those sulfur, nitrogen, and as well as carbon in the fuel sources, again, particularly from coal, those components get oxidized into in the atmosphere. They become SOx or NOx. We'd use that X just to say varying number of oxygens, levels of oxidation, and CO2, the carbon monoxide or carbon dioxide. And when those species, nitrate, sulfate, and CO2 interact with water. They actually make nitric acid, sulfuric acid, and carbonic acid. Each of those acids, contributes to the acidity of water, can degrade soils, can weather buildings, can kill fish, and can have a whole variety of other, denudation of surface material. So it can be really bad for soils, ecosystems, and particularly aquatic ecosystems. In general, nitric acid and sulfuric acid rapidly acidify precipitation. And as we said, they, in addition to degrading soil, leaching metals like aluminum, they also degrade the nutrients, and are a pretty large economic problem, as well as environmental problem in the United States. Today, most of the problems are in the areas of the Great Lakes in New England. Sorry, not the Great Lakes. Apologize. Most of the coal burnings in the Great Lakes region in Illinois, Indiana, Ohio, Pennsylvania, Kentucky. Most of the problems where acid rain occurs is actually in New England and the Adirondacks. The main issue there's two factors that are important in why you see the pollution having such impact downstream. The first is the fact that the aerosols cut out, they get in the air, they blow with prevailing wind directions. Some of them do fall out right here in Ohio or in Illinois, Indiana. But we have the luxury of having very carbonate-rich, glacial-rich soils in this area, and they have the capacity to basically neutralize the acids and minimize the impact of acid rain in these areas. Glacial till is a big part of that, as well as the carbonate platforms. As you move further to the east, and particularly the northeast, you run into areas that are igneous and metamorphic. Those have limited capacity to buffer the acids of what's called a lower cation exchange capacity. As a result, acid rain has a more profound effect in those regions. So it's both the geology and the surface, the chemistry of the soils and rocks, as well as the fact that it takes a while for these things often to rain out in rain events or snow events, or the case may be. So moving on to the specifics of coal. Coal is produces as the result of incomplete degradation of buried organic plant matter. You'll often, if you look at a coal, if you find a sample of coal, you'll see leafy ferns in there, and the fossils will tell you it's very near surface, or actually even sometimes on land in swamps or something like that. The bituminous coal is the most common type of coal. It's a lower thermal maturity, which actually is a lithified rock, typically more than 50% carbon. Anthracite is actually the highest grade coal, commonly is well more than 80% carbon, and actually is, for that reason, is low, also low volatiles, and commonly used as a thermal coal for metallurgy or steel refining, stuff like that. Some of the biggest problems with coal mining, of course, are the fact that coal mining is most economic by doing strip mining or mountaintop removal. These are areas, as I showed you pictures in the slides, where they literally come out, remove all the vegetation, all the surface area. They dig down into the rocks, and they just take layer after layer after layer. Some of the problems, of course, is you're completely removing ecosystems and habitat. You're often exposing metal-rich fluids that can create acid mine drainage very readily, and increase the rate at which those reactions occur. You're also commonly taking that debris and filling in valleys nearby, which can lead to slurries, dams that can fail, or just otherwise change drainage systems. So it's sort of a worst case scenario for an ecosystem. It's almost amounts to complete and total removal. So in terms of coal mining, the impacts are numerous, but they include acid mine drainage, when these reducing sulfur components that are distributed in rocks actually get in contact with oxygen-rich water and air. They get oxidized sulfuric acid, make that orange. They make acidic waters, which actually leach metals that create the orange and yellow colors. Acid rain can be related to nearby mining operations, or more commonly from power generation using coal. There's obviously slurry releases or dam failures, sludge flows, dam breaks, which actually can remember the Kingston flood in Tennessee. They actually put a wall 25-foot high of sludge and ash out of the area and down through the valleys. I mentioned mine fires, as well as toxic metal releases from both the coal burning, coal mining, and also, I think it's not both, from coal mining, coal burning, as well as acid mine drainage. So, but remember, coal, big idea here, still the #1 source of electricity power generation in the U.S., even more so in places like India and China. In the U.S., the price of natural gas has basically been the biggest thing to put a dent into, coal combustion. Onto oil and gas. Natural gas is typically cleaner burning than coal. That's true. There are other environmental impacts of oil and gas development, particularly natural gas development, related to methane leaks for greenhouse gases, related to fugitive gas releases. Nobody's claiming it's not a fossil fuel, but the reality is it is cleaner burning than coal, even though there may not be, the benefits might not be entirely related to greenhouse gases. There's still a lot of less metals, acid mine drainage, things like that that are released. In terms of the biggest development in oil and gas, there's been a long history of conventional drilling, going to those traps and putting a well in and sucking gas out. Coal bed methane was hydrates. Coal bed methane was a resource where shallow coal beds were drilled. Microbes generate methane from the coal, and people try to sink wells in them and harvest methane. Hydrates have been an area that people have looked at offshore, but really the biggest fundamental revolution in natural gas has been around hydraulic fracturing targets of shale rocks. That relies upon, as I say here next, doing horizontal drilling, so you can directionally drill and maximize your contact within a source rock, as well as actually increase the pressure through hydraulic fracturing in that source rock, open up the porosity in production, and make the energy that potentially there accessible, so it can be extracted from shales and other conventional resources like tight sands. Those things in combination have made hydrofracking probably the biggest topic of the last decade or so, and clearly the biggest thing that's happened in energy in quite a long time. As I mentioned, there are now thousands of years of natural gas resources that are tappable by virtue of using this process all over, North America and throughout the world. Again, cleaner burn than coal, although still is a fossil fuel that releases CO2, and there is that implication to deal with. As I mentioned with coal, oil and gas is formed by incomplete degradation of buried organic matter, although oil and gas is typically derived from organic matter produced by bacteria, plankton, as well as algae. On the forefront of where oil and gas field is going, there's still a lot of debate about this, but tar sands, particularly within Canada, are immature shales that need to be heated up in order to generate oil. They're typically mined like a surface mining or a mountaintop removal mining process, heated up locally to make the oil the right constituency they want. And then the idea was to put in a pipeline and send it down to different areas for refining, including on the Keystone Pipeline to the Gulf Coast of the United States. So, very controversial in the sense that they are expensive, very polluting, have a huge water demands, and lead to a great amount of contamination potentially when this occurs. On the topic of this, one of the other environmental impacts is that methane can be released to groundwater. Is one of the most common environmental impacts from shale gas development. There's a clear understanding there's a lot of methane contamination in petroleum basins where drilling occurs. There's still a lot of debate as to whether that methane contamination is naturally occurring or caused by faulty well casings, leakage through the borehole or the annulus. But it remains one of the most controversial things related to oil and gas generation. The other aspect that you have to consider with the oil and gas, we talked about acid mine drainage, we talked about mountaintop removal, we talked about all these myriad of problems that occur from coal mining. They're big, they're problematic, and they need to be dealt with. But oil and gas is not immune from those sort of long-term derivative problems. One of the major issues is that the price point of coal is largely dictated by how far you have to transport it and how much water is needed to clean it and prepare it. In the case of oil and gas, it usually comes down to access to pipelines, right? It's a fluid, it can flow through a pipeline. It tends to be a lot safer than hauling things in trucks, much more economic than hauling things in trucks. But the reality is those pipelines represent a major vector of environmental concern related to oil and gas. Pipeline leaks are often caused by corrosion, an outside force or impact. Somebody hits them intentionally or unintentionally. But when those pipes break, they are major incidents. So I brought this up in the lectures. There's about 30,000 major incidents in the last 60 years. The annual cost of these things is in the billions of dollars per year. Many, your average leaks, you're talking about $1 million problem. They can be, they're designed to transport fluids at high pressure and high volumes, and the result when there's a break, a lot of fluid can be released out into the environment and can be quite devastating. So on the topic of mineral resources, the third sort of, I suppose, major topic of material that'll be on this exam, mineral resources are fundamentally important. It's probably a much bigger area of geology than either water or energy, even though people don't necessarily think of it like that. But minerals are essential for technology, for like electronics, building materials, which is the biggest use of mineral resources, chemistry, feedstocks, and agriculture. Like I said, building materials make about 94% of all the materials that are mined every year. That could be quarries, road aggregate, building materials. That's a big issue for this field and mineral resources, and employs a lot of geoscientists every year, and has a lot of associated environmental geoscience monitoring aspects. So all of these combined are the mineral resources we're going to focus on. Remember this adage. I won't test you on this quote, I promise you, but if you can't grow it, you have to mine it. And the reality is, a lot of the resources we use are based on mining resources. If you think about the image I showed you in class with the highway, with the cement roads, macadam, the paved roads, the cement barriers, signs and cars, everything you see other than the people sitting there are literally mined from something. So what do you mine? Typically speaking, most of the economic geology mine deposits are based upon identifying the location of ores. An ore is a rock with a valuable, in which a valuable or useful metal or other material occurs at concentrations that are sufficiently high relative to average surrounding rocks to make it economically worth mining. So the key aspect here is you need something where there's a high concentration of a particular process. We didn't go into this in much detail in the lectures, but typically these are enriched by things like geothermal deposits, volcanism that heat things up and mobilize fluids. And in some cases, you can find an ore that has really high levels of gold, sometimes 1,000 times more richer than in gold than surrounding rocks. But all of that depends upon a few factors. The value of that ore, of any ore, is determined by its concentration, how much of it's in there, how much gold's in the rock, and the current price of the resource. I use the example of lithium. In the 1950s and 60s, it was worth almost nothing, and now it's considered one of the most valuable commodities because of the spot price and demand for energy storage and batteries and things like that. If I'm gonna give you a handful of numbers, I really want you to know, this is one of them here. Each year, more than 45,000 pounds of materials are mined per capita in the United States. So that means that per capita, every single year, you have about 45,000 pounds of materials either mined for your use or on your behalf. Obviously, a lot of that is infrastructure, roads, buildings, etc., which is a pretty astounding number in my mind. The other number I've used so far, I'm going to highlight again for you, is about 10% of the power production comes from renewables, and that number really hasn't changed. I alluded to this with the mining resources, that building materials for construction, roads, road aggregate, that makes up about 94% of the material that's mined in the U.S., and that number isn't going to get any smaller. It continues to be a major area, even though our economy is not booming like it once did. This is where we're seeing most of the mining materials go. The per capita usage is largely based on this. Highlighted this in terms of the mineral resources. Rare earth elements, we mentioned the fact that it's a bit of a misnomer. They're not actually rare, but they are dispersed and do not occur in ore deposits. The exceptions are that they're very insoluble in water, and as a result, they tend to bind preferentially to clays. So you find areas where there's large amounts of clay deposits. They can be modestly enriched in rare earth elements. Perfect examples of this are clay deposits related to the Himalayas in China. And another number I want you to remember is that despite the amazingly important role of rare earth elements in electronics and healthcare, but particularly in electronics, almost all of, more than approximately 97% of all the rare earth element minerals in the world are mined in China alone. And as a result, it's a really important political issue, geopolitical issue around this resource. Most importantly, rare earth elements, I can't stress enough, essential for the electronics industry. Your computer, your cell phone, all these things rely upon access to rare earth elements and rare earth element magnets. We talked a little bit about this. Rare earth elements, the price has incredible volatility. It's been extraordinarily high, back to the intermediate now, with many ups and downs between, competition from all sides. When something becomes valuable, one of the lessons here is that the price goes up. It's basic economics. But what was sort of unforeseen is that many of the countries of the world sort of responded with programs to develop rare earth element resources. But also, what more critically impacted the price was the fact that you started to see, artisanal mining or local mom and pop shops where people were going out there mining this, purifying this. And let's be honest, the scary part in my mind of that scenario is that those folks probably don't have a background in geology, chemistry, metallurgy, and as a result, it's not clear that they're not putting themselves at great risk for health impact by virtue of preparing these ore deposits or non-ore deposits, in the case of earth elements. But areas, earth elements moving forward remains a big geopolitical issue. A lot of concerns that it's going to continue to be a problem. But there's all kinds of strategies ranging from space exploration to the bottom of the oceans to obtain these things to make sure that it can't be used as too much of a political football. So those three topics, the last part of stuff on water quality, energy for coal and oil and gas, as well as mineral resources, are the bulk of the exam. I think it's about 20 to 30 questions. What I have next here is a list of just key themes, and nod, wink, wink, hint, hint. These key themes are things I think you might see on your exam. But a couple of key things I want to highlight here is that population growth is the greatest threat to sustainability and the greatest threat to society. Quite frankly, the carrying capacity of the Earth is probably past its limit. We've had to get really creative and become really good engineers and scientists and policy folks to sort of keep everything together. If there's anything that scares most people and all scientists, it's this inexorable rise to about 10 billion people. It's hard to know how we're going to feed the future, how we're going to provide water for the future, and how we're going to provide energy and research the future without going into an absolute runaway greenhouse gas emissions problem, which we might already be in. So these are some of the themes that are important. I want you to know some content related to that problem. That was an underlying key theme from the first lecture: population growth and sustainability. One of the other reasons that population growth is so dangerous is the fact that you can't have that many people without pollution. Hazard waste management becomes a major issue. There's also the risk of extreme impact from natural hazards. We used the example very early in the semester of Port-au-Prince in Haiti. You get all the people living in an urban area. When you just happen to have an earthquake in that area, the amount of lives lost, the amount of medical, health, damage and whatnot can become, extreme. And of course, the last component of that is the overexploration of non-renewable resources. We have a finite amount of oil, coal, natural gas. We might want to go away from them. We might want to get the solar. I think we all do. But the reality is we're not there yet. And the balancing of these non-renewable resources has an important role in thinking about sustainability. And quite frankly, their use has an important role thinking about sustainability in terms of greenhouse gas emissions. A couple of facts about the age of the Earth I want to highlight that you should know. One is that I want you to remember, basics of the age of the Earth. The age of the Earth is about 4.56 billion years old. We talked about the fact that there was a lot of debate early on in science about just how long it took the Earth to form. Now, based on radiometric age dating, people accept that the age is about 4.56 billion years old. How does the Earth actually sustain heat? This is interesting compared to a lot of other planets that aren't inhabited. Is most of the heat in the Earth comes from radioactive decay of uranium, thorium, potassium. I won't test you on those elements, but radioactive decay is important, as well as crystallization. The process of magma moving around the Earth that crystallizes releases heat by an exothermal reaction. Then, of course, there's actually some heat still trapped in the Earth at the time it formed during the Earth's formation. Together, those three factors actually provide most of the heat on the Earth. Solar radiation keeps the surface warmer, or prevents it from being warm, but actually is a bit of a tail wagging tail on the dog rather than tail wagging the dog. And then, your plate boundaries. Convergent boundaries are moving together, divergent are moving apart, and transfer moving past each other. That's probably about the level at which I want you to remember that. But I think you should probably commit those bits of information to your memory, and consider them as you move forward. Convergent, divergent, and transform are also the three sort of types of plate boundaries you really have to make sure you wrap your mind around. And then geohazards, we went through a variety of them, spent a lot of time on this in different aspects. Volcanoes have a whole myriad of geohazards, including poisonous gases, debris flows, lava flows, ash falls, tsunamis, which I failed to mention here, pyroclastic activity. Think of all these hazards when you're thinking about volcanoes. They're incredible resources in terms of the energy they provide and geothermal energy, metals that they enrich in ore deposits, but there's a lot of associated hazards next to living near a modern one, as well as changing climate, as we talked about as well. If you can probably guess, this type of question that shows up on a which of these various things fit in the hazards kind of things, or in all the above kind of things. I'm feeling generous at the end of the semester here. We talked a bit about coastal hazards, particularly hurricanes. That's the one I want to highlight. Obviously, climate change and intensification of hurricanes by really warm waters in areas like the Gulf of Mexico play a role in exacerbating the extent of hurricanes. But some of the other things that are generally true, even if we solve that problem, is that population growth, sustainability, as in sustainability effects and has, major effects on natural hazards, the expansion of pervious surfaces, urbanizations, putting impervious surfaces where water can no longer flow into the ground and dissipate some of the flood waters, loss of vegetation, particularly erosion in resistant vegetation like switchgrass, along with that storm intensification, they all exacerbate the impacts of hurricanes. So, if you want to keep this in mind, there aren't that many more hurricanes than used to be. There are more intense ones, but the biggest issue with the hurricanes we've had in the last few decades is actually, particularly the last decade, has actually been related more to these top things. It's related to more people being in coastal areas, being more densely populated in the coastal areas, seeing more expanse in impervious surfaces, and the loss of erosion-resistant vegetation, which allows the amplitude or the flooding related to those hurricane efforts to be greater. Even if it's not a hurricane, this aspect of urbanization increases the magnitude and the frequency of flooding because water can no longer infiltrate the surface, in the subsurface, in the groundwater. As a result, whenever you see a situation where water wells are backing up or where this gray water discharge is backing up, you can see massive flooding that takes sometimes days or weeks to see removed. Again, I'm not going to touch you on every aspect of all these, but the ones I'm highlighting here are there for a reason. I'm over stressing the fact that I want to make sure you focus on them. Drawdown of groundwater, such as that observed in California and the High Plains Aquifer, has a lot of effects. Oftentimes, the biggest issue is that it's irreversible because subsurface subsidence causes the grains to collapse and the aquifer can never be recharged. So this can be really important for the drawdown of, as a hazard from drawdown of groundwater. Next, I'm just going to go over some example questions. What category of mineral resources account for the largest fraction by weight mined in the U.S.? It's building materials. Remember that metals, agriculture, and chemical feedstocks are all relevant, but building materials, 94% comes from that aspect alone. Rare earth elements, despite the fact that they're relatively abundant, were originally thought to be rare. It's because they really didn't occur in any ore deposits. There were small amounts everywhere. As a result, people didn't really detect them very easily. As a result, they got the name misnomer rare earth elements. We talked about oil and gas development. Hydraulic fracturing typically targets which hydrocarbon-bearing rock formation. It's typically going to be shales. There are some other unconventional aspects, but shale is the one you want to look at on a multiple choice exam. Which form of coal contains the highest percentage of carbon and generally lowest percentage of volatiles and moisture? Remember, peat, lignite, bituminous, anthracite, you see decreasing amounts of volatiles, increasing amount of carbon, and increasing amount of energy per unit of rock. And then finally, the last question here, which we had as an example, is which of the following are major hazards associated with volcanoes? Poisonous gases, debris flow, lava flows, ash falls, pyroclastic activity, or all the above. Hopefully, at this point, you're all recognize that's certainly an all of the above kind of answer. These are just some examples. I can't promise you these will be on the exam, but they're at least close, or there'll be things that I think are important and could be an exam. So just to recap, 30 questions, multiple choice, true, false, very short answer that will done be multiple choice. A little bit of the water quality, particularly on naturally occurring contamination, arsenic, particularly in Bangladesh, and some naturally occurring methane. Talked a lot about the basics of energy consumption. Numbers I like: 10% of energy produced by renewable energy resources. Hasn't really changed. CO2 emissions use have actually gone down as a result of changing power distribution. Oil and gas and coal are both important resources for energy production and transportation. And mineral resources, again, 45,000 pounds of materials are mined per capita in the U.S. Each year, while building materials are the most important component of that. I don't think you'll have any trouble with the exam. I expect if you've done well this semester, and most of you have done very well this semester, I suspect you'll continue to do just as well as we move forward into class with the final exam. Again, it'll be open on Friday. Right after Thanksgiving, you can take it. don't want anyone thinking about this over Thanksgiving. Have a good holiday, but it's available if you can do it as flexible as you want. Everything should be ready for the rest of the semester. This will be the last you hear from me again. It's been a pleasure meeting those of you I've met and teaching those of you I've managed to connect with. I look forward to hopefully seeing you more in some earth science classes in the future. Have a great, I hope you've had a great Thanksgiving or are about to have one, and I hope you have a great end of the semester and a peaceful transition to the new year, which hopefully will be COVID free at some point. Thanks.